Hey everybody, welcome for coming to our presentation of Umbra, our real-time collaborative programming application. The Umbra team is made up of David Dickinson from California, Fred Durham from Texas, Michael Johnson from Oregon, and Bethany Pietroniro from New York. So, what is Umbra? Umbra is a browser-based code editing and evaluation tool for quickly and seamlessly collaborating on code in real time. Umbra's emphasis is on being unusually lightweight and convenient, while still offering robust functionality to effectively support our targeted use cases. One thing that sets Umbra apart is the speed and ease with which you can start collaborating. Just follow these 3 steps. First, go to the Umbra homepage. Next, copy the unique room URL and share it with your coding partners. Then you're all set to either paste in some code you've been working on or begin crafting new code together on the spot. The core functionality of Umbra allows users within a single browser window to access real-time collaborative editing, secure code evaluation, and support for multiple programming languages. Umbra's core features are available to everyone, no account needed. But if you do decide to sign up and log in, you'll unlock the ability to save your code snippets in a personal library, adding a layer of convenience for future sessions. Who can benefit from using Umbra? Umbra is tailored for learners picking up a new programming language and professionals seeking for a streamlined, collaborative coding space. It's versatile for various scenarios, such as students receiving immediate guidance from mentors, developers engaging in efficient pair programming remotely, and companies conducting coding interviews without any hassle. In our research, we were captivated by the surge of innovation in real-time collaborative editing. We imagined a tool that combines the simplicity of Excalibur or Google Docs with the power of a programming environment, complete with the capability to run code and see results instantly in the browser. Our research into existing solutions revealed that most tools specialize in 2 out of 3 key areas: real-time collaboration, in-browser code execution, and a lightweight, simple setup. For instance, platforms like Glot.io and Valtown excel at providing runnable code through shareable links, yet they lack features for collaborative editing. Conversely, services such as CodeShare support real-time collaborative editing, but don't offer the capability to execute code within the browser. Then there are comprehensive IDEs like VS Code, LiveShare, and Replit, which combine real-time collaboration with code execution. However, they often introduce complexities such as mandatory user accounts, initial setup overhead, the need for consistent local IDEs among collaborators, or access behind a paywall. While these existing applications provide a wealth of features, our aim was not to supplant them, but to build a tool that resides at the optimal intersection of real-time collaboration, in-browser code execution, and a streamlined setup process. Umbra is well suited for such use cases as debugging a function, sharing methods for refactoring code, assisting with technical interview preparation, or any scenario that benefits from immediate collaborative editing and code execution, where the need for a full-fledged IDE environment is secondary to the convenience of spontaneous collaboration. Behind Umbra's intuitive interface lies a robust technical framework designed to deliver a smooth user experience. Let's explore 3 foundational aspects: real-time collaboration, secure code execution, and scalability. First up, real-time collaboration. Umbra harnesses CRDTs, or conflict-free replicated data types, to enable users to edit documents together without stepping on each other's toes. It's like what you see in Google Docs. Everyone's changes are integrated instantly and harmoniously. Next, we prioritize security in code execution. Umbra utilizes containerization to safely run the code our users input. This technology acts as a strong barrier, significantly lowering the risk of security threats from user-submitted code. Finally, scalability. Umbra is built to scale smoothly with a distributed backend system. This means that as more users join in, Umbra keeps up, maintaining its quick performance and low latency without a hitch. Before we dive into the construction of Umbra, let's set the stage by exploring what real-time collaborative editing looks like in web applications today, and take a quick journey through the history that paved the way for it. Collaborative software is essential for teams to achieve common goals effectively. Examples include electronic calendars for efficient scheduling, project management tools for streamlining team coordination, and platforms like GitHub for collaborative source code management. These tools typically operate asynchronously. You might send a calendar invite to be accepted at the recipient's convenience, update a Jira task for later review, or create pull requests on GitHub that are merged following a thorough check, rather than in real time. Real-time data is integral to the tools we rely on every day, delivering updates that seem to happen the instant they occur. Consider weather apps. They're constantly updating to give us the latest temperature and conditions, mirroring the live environment almost to the second. Or take a look at stock trading platforms, where prices tick up and down in a live feed, giving traders the pulse of the market so they can make quick, informed decisions. Such immediate data synchronization is crucial, enabling users to make decisions and act based on the most current information available. In a real-time collaborative editing application, our aim is to replicate the feeling of co-presence, to evoke the sense that you're working side by side with others. It's about creating an experience where collaboration happens as naturally as if you're in the same physical space or using the same computer. Real-time collaborative editing enables multiple users to concurrently modify the same document or dataset over the web. This concurrent editing capability is complemented by the system's ability to merge and display changes from all participants in real time, facilitating an almost instantaneous collaborative experience. Over the last 50-plus years, real-time collaborative editing has evolved from a visionary concept to a mainstream tool. With the mother of all demos in 1968, Douglas Engelbart introduced the idea of collaborative computing, including real-time text editing. The early 2000s brought applications like MoonEdit, which demonstrated practical collaborative editing over the internet. And the mid-late 2000s saw Google Docs bring collaborative editing to the web, widely popularizing it and integrating it into common productivity suites. Now, let's shift our focus from the milestones of the past to the present, where we can see the culmination of these advancements in action. Here, we can see two anonymous users of Umbra, perhaps in different parts of the world, working together on the same document at the same time. Each person's contributions are merged seamlessly and almost instantly, allowing for a dynamic and interactive workflow. This technology transforms solitary tasks into collaborative projects, enabling a group of users to edit a file simultaneously and see the updates as they happen. Now, the core technical challenges in enabling effective real-time collaboration revolve around three key areas. First, conflict resolution. How do we handle simultaneous edits at the same location in a document? Or reconcile changes after a user reconnects following a network issue? It's crucial that all users have a consistent view of the document. Secondly, awareness broadcasting. Each participant needs to be aware of the others in the session, understanding who is making changes and where, striking a balance between being informative and overwhelming. Last, latency minimization. Updates to the shared document should be swift and reliable, ensuring that what users see is up to date and accurate. Let's begin by examining conflict resolution. In a collaborative editing application, which operates as a distributed system, each user interacts with their own replica of the shared document. This means multiple copies of the document exist simultaneously. Users can edit their copies of the document at any time, which naturally leads to temporary discrepancies between versions. The emphasis is on temporary, because for a robust, real-time collaborative application, it's essential to guarantee that all versions will ultimately converge to a unified state. We've implemented eventual consistency using conflict-free replicated data types, or CRDTs. These are specialized data structures with built-in conflict resolution, allowing conflicting changes to be reconciled algorithmically without relying on a central server. CRDTs track which user made a change, where in the document they made it, and when they made it. In addition, though, CRDTs assign each change a set of globally unique identifiers that further define its context and content. These unique identifiers within CRDTs are crucial for maintaining their commutative and associative properties, ensuring that regardless of the order or grouping in which changes are applied by various users, the final state of the document remains consistent. This is a fundamental aspect of CRDTs that allows for seamless real-time collaboration. Additionally, CRDTs are designed to be idempotent, meaning that duplicate operations, like multiple users attempting to delete the same character, will not cause any unintended additional actions. With CRDTs, all conflict resolution happens algorithmically at each user, without the need for a central server to be arbitrating. As we will see later, Umbra does use a central server, but its role is more like a postman than a judge, acting to relay CRDT-based updates between users, who then each apply the CRDT merge algorithm to their local copy, each converging to the same final state. CRDTs enable distributed editing and real-time collaboration without the need for a central authority, but this does come with certain memory and processing trade-offs. As shown on the left, CRDTs keep deleted characters as tombstones in memory to maintain consistency, leading to increased memory usage. The chart on the right illustrates the performance implications of this approach. In JavaScript, as the count of objects grows, the time required to create new objects rises exponentially. This stems from JavaScript's object model, where objects are essentially key-value maps, and maintaining a larger set becomes increasingly complex. This underscores the importance of optimizing CRDT implementations for practical applications. CRDTs offer a decentralized approach that we found attractive, but we were conscious of these potential performance drawbacks. So our search led us to YJS, a robust, open-source CRDT framework that inherently optimizes performance. The key to YJS's efficiency is its strategy of consolidating numerous related text insertions into a single composite change item. This approach significantly reduces operational costs and memory footprint. YJS is tailored for real-time collaborative text editing, supporting a dynamic range of extensions for various network configurations, data storage solutions, and text editor integrations. Moreover, YJS leverages CRDTs to maintain and manage user awareness, allowing participants to observe each other's actions seamlessly as document changes are synchronized. Now, I'll hand off to Bethany, who will explore the transition from a standalone front-end code editor to collaborative code editing.
Thank you, David. So, Umbra's frontend is a single-page application written in React. We use a dependency called CodeMirror for text editing. This is a code editor component that manages its own state independently of React. The CodeMirror component is where our users type their code, as you've seen in the demos in previous slides. User inputs such as keystrokes and copy-paste actions are processed as data transactions within the CodeMirror editor. CodeMirror has a steep learning curve, but once you learn the interface, it's highly configurable, so it can be customized for all your desired code editor functionalities, such as syntax highlighting. But the real challenge is then to move from having a single user code editor to one that allows for real-time collaboration between multiple users. So how can we take this editor component and integrate it with YJS to serve as a multiplayer code editor? The full answer to this involves some layers of technical complexity, and that could provide the content of a whole presentation on its own. So for present purposes, we'll stay at a relatively high-level view, and we'll start by introducing a few key tools. Achieving a collaborative CodeMirror instance involves integrating some libraries and modules that are part of the YJS ecosystem. One is called YCodeMirror Next. This module binds YJS's CRDT functionality with CodeMirror's built-in state management. YCodeMirror Next was built specifically to track changes within CodeMirror and also to manage undo and redo actions so that users don't actually accidentally undo each other's edits. So this gives us a handle on the contents of the editor and also helps to funnel the content of the editor into a CRDT data structure. As a quick reminder from the previous section, CRDTs are data types that are built to facilitate collaboration by resolving conflicting inputs algorithmically. Additionally, we leverage the Y protocols library from YJS. These protocols help us listen for document updates and integrate changes. They also allow for awareness information to be updated and displayed so that users can see each other's names and cursors, for example. Now that we have the editor window all set up, we're tracking state changes with CRDTs, and we're able to integrate updates from different users. The next step is to actually transmit and receive those updates over the internet for a real-time user experience. We used a WebSocket server to do this, along with a corresponding module from YJS, unsurprisingly called YWebSocket. So the WebSocket protocol is a standard choice for real-time web applications. It allows simultaneous two-way communication over a single TCP connection. On top of standard WebSockets, YWebSocket encapsulates the standard WebSocket protocol and sets it up to manage its own backup copy of the CRDT-based shared document that we use. To get a specific idea of how Umbra leverages WebSockets, imagine two users, Alice and Bob, who want to do some coding together. When Alice first navigates to the Umbra homepage, a new WebSocket connection is opened, and she is rerouted to a URL that represents a unique WebSocket room. When she sends this URL to Bob and he navigates to it, Bob is routed to the same room. So what this means is that whenever our WebSocket server receives updates from Alice from then on, it will broadcast those updates to Bob and vice versa. And the same applies when there are 3 or more users in the room. So zooming in a little bit more, what are these updates that are being sent, and how does our WebSocket server manage them? In the context of our application, a WebSocket room corresponds to a single shared document, which is represented in memory as a CRDT-based data type called YDoc. That's from YJS. YDoc is the top-level shared data type in YJS, and it contains all the data and state for a collaborative session. All users who are connected to a specific WebSocket room are contributing changes to the same YDoc whenever they make edits in the code window. When a user first joins a room, WebSocket sets up a WebSocket provider for the user, encapsulates the YDoc within the provider, and sends the current state of the shared document to that user. Then, whenever a user makes a change to their YDoc by typing or undoing or pasting, the update is sent to the WebSocket server, and the server propagates that update to all other users in the room, again with the help of Y protocols under the hood. The same process happens with awareness information. Okay, so far, most of the functionality we've talked about, we were able to achieve just by using the WebSocket protocol and the tools that we mentioned from the YJS ecosystem. But we still needed a few more solutions. First, allowing data persistence. We needed a way to persist document state, even if just temporarily, so that updates would be preserved and transmitted eventually in the case of network disruptions or server failure. Second, we needed integration with our front-end technologies. Getting YDoc and code mirror updates to play nicely with React state management turned out to be a bit tricky, and it required careful implementations of custom state and effect hooks. Finally, scalability. We wanted to be able to scale our collaboration service to accommodate increased user and document loads, while maintaining low latency for conflict resolution and efficient use of server resources. As we researched ways to tackle these challenges, an open source project called YSuite emerged as a compelling toolkit. YSuite is a suite of packages designed specifically for developing production-ready YJS applications. It consists of three major components. First is the YSuite server. So this server actually extends WebSocket, which we saw before, and it also uses the Rust port of YJS to deploy as a WebAssembly module on Cloudflare's edge. So the Rust language is known to be high performance, and Cloudflare's edge network is purportedly within 50 milliseconds of 95% of the world's population. So together, these factors enable low network latency for our application in various on-demand locations around the globe. This deployment strategy uses a serverless approach to horizontal scaling, and Michael will discuss that in more detail later in the presentation. Then there's the YSuite SDK. This is a TypeScript library that facilitates interaction with the YSuite server from our application's backend. It provides various utilities like functions to create and manage documents and client tokens that authorize document access. Finally, there's the YSuite React library. So this React hooks library greatly simplifies the process of integrating YJS into our front end by helping us coordinate React state and effect hooks with the CRDT-based data types provided by YJS. So that was a lot of information. That's it for now for the overview of our collaboration service. I will turn it over to my colleague, Fred, who will talk about how we implemented secure code execution.
All right, thanks, Bethany. Let's move on to code evaluation. So one of the core functionalities of Umbra is that users are able to run the code that they write. But where should the code evaluation actually occur? And how can we execute that untrusted code safely? When it comes to considering where to execute user code, the two options we considered were running the code in the client browser and executing the code on a server that we could build for that purpose. Executing code on the client side has certain things to recommend it. One of the major advantages of that approach is that it removes the need for the network trip that's involved in communicating with a remote server. And this allows for reduced latency for the user. Additionally, by running code in the client's browser, we would have one less backend service to build, host, and manage. We also don't have to worry about how untrusted and possibly malicious code could affect our system since it's run locally. But what are the downsides to client-side code execution? Well, first, it places additional load on user system. Second, it reduces our ability to observe and control the code evaluation performance. And finally, using client-side code execution makes the ability to support multiple programming languages much more complicated. By default, using the client browser for code evaluation would have limited us to a JavaScript-only application. Adding support for languages beyond JavaScript would have necessitated compiling user-submitted code down to WebAssembly formatted bytecode, which involves extra processing steps and additional complication. So what about server-side code execution? Executing code on our own server has several advantages. First, one that is important for our use case, evaluating code on the back end allows us to easily support multiple programming languages. This can be done by simply installing the correct compilers or interpreters on our server and writing the logic to route user-submitted code to the correct one. Second, having our own code execution server means that we have more control over the execution environment, which we will see is helpful for security and observability, among other things. The trade-offs of evaluating code on the server side include the network round-trip latency introduced by having to communicate with a remote server, and the fact that we would be running potentially malicious code on our own server. In the end, we went with server-side execution of user code. And this was by far the most straightforward solution for handling multiple languages. And while it does present the possibility of security dangers, it offers us plenty of control over how to deal with this issue. And there are many tried and true solutions for just such a scenario. Before we take a look at the particulars of our code execution server, let's take just a moment to consider what security dangers are posed by executing untrusted code and what can be done generally to help secure servers that must run untrusted code. One possible danger is that of depleting host system resources. Generally, either on purpose or by accident, user code can potentially use up compute, memory, disk space, or network bandwidth on a host machine, which can cause slowdowns or crashes and buffer overflows. Data breaches are another concern. This sort of vulnerability occurs when malicious code can be run that elevates the user privileges or circumvents authorization safeguards in some way that allows access to existing data on the system, but was not meant to be available to the user. One last example is the possibility of network integrity issues. Executed user code can appear to be acting from within the host system instead of outside of it, and accordingly, it might be able to bypass existing network and service restrictions that were put in place. A very common approach to securing a system against security vulnerabilities like these is known as code sandboxing. Instead of giving a user access to the standard capabilities of a computer, they get access to a sandbox, an isolated environment that insulates the host system from the code being run. This isolated environment generally consists of an emulated operating system that is configured in such a way that access to the underlying host file directories, system resources, and OS operations are not possible. This means that any malicious code could only damage this emulated environment and not the underlying host. Two of the most well-known ways of sandboxing are virtual machines and containers. A virtual machine is a more heavyweight solution that involves emulating both the hardware and operating system of a computer, whereas containers run on top of the host computer's operating system and utilize its kernel to provide separate container environments. With all of this in mind, for Umbra, we chose to use Piston, which is a general purpose code execution engine that supports over 80 programming languages. It provides secure sandboxing by way of containerized code execution. In addition to containerization, Piston achieves further security by executing each block of code in a temporary virtualized directory and allows us to set limitations on what effects that code can incur. It allows the specification of maximum running time, compile time, and memory used, among other things. In addition to these first two layers of security measures, Piston hardcodes additional steps to confront other common security threats, providing what is hopefully a redundant third layer of security. So a few examples, What it could prevent would be fort bombs and file-based attacks, disk space attacks, runaway output, unauthorized data transmission, and privilege escalation. These are a few of the threats that are specifically accounted for just in case the more general layers of security sandboxing could somehow be circumvented. Well, that kind of wraps it up for the code execution section. Let me go ahead and hand it over to Michael to talk about our system design.
Thanks, Fred. So before concluding, let's take a look at the hosting considerations and system design for Umbra. Some of what I'll talk about here will be review, but it will be review with an eye towards having an overview of how Umbra works as a whole, as well as zooming in on some system design decisions that we had to make. So let's start with some general considerations. In designing the system architecture, we prioritized separation of concerns and scalability. And for these reasons, all of Umbra's major functional components are served from their own dedicated nodes. The overall result of that is a service-oriented architecture that's flexible and loosely coupled. We wanted to ensure that as the application evolves, we can make changes to a particular service's code or its hosting infrastructure with minimal consequences for the other services. All of Umbra's non-managed services are containerized using Docker containers and deployed automatically via GitHub Actions to their various hosting solutions. Having everything in containers like this was a big advantage for prototyping flexibility and ease of development workflow. These containerized services are currently deployed via AWS Lightsail instances. Lightsail is a cloud platform that's built on top of AWS EC2 that streamlines some common tasks, such as deploying a container from Docker Hub, at some cost of decreased configurability. Lightsail has afforded us greater development efficiency by abstracting away concerns that we would otherwise handle manually, such as port mapping and SSL or TLS encryption. Additionally, Lightsail provides powerful and simple container deployment options, simplifying both manual and automatic container deployment. With that out of the way, let's look at the major components of Umbra's service architecture and review their roles, starting with our web server. The hub of Umbra's backend services is the web server, which is responsible for routing and responding to HTTP requests to our website. For many requests, the web server will communicate with other services to develop an appropriate response to send back to the client. The web server has some level of connection to every other service in our system. So here's an overview of the communication flows handled by the web server. First, communicating with the code execution server. When a client wishes to run some code that they have written, the web server will send the code and its metadata along to the code execution service, which evaluates the code and sends back the results. Second, the database server. When a signed-in client sends Umbra a request to save a block of code to their code library, the web server initiates a request for a write to our AWS RDS Postgres database. Third, the user authentication server. For this, the web server communicates with an AWS managed service called Cognito. And lastly, our web server helps to initialize the initial connection between users and our collaboration service. Let's double click on a few of these services and talk about what trade-offs were considered when deciding on their technology stack and their role in Umbra's architecture. While doing so, I want to give particular consideration to how scalability influenced our decision-making. As Fred highlighted earlier, for both reasons of security and scalability, code execution takes place on its own server. Like the web server, the code execution server is one of the services that's containerized and deployed to AWS Lightsail. Right now, it's deployed as a single node, but down the line, we would scale it horizontally in tandem with the expansion of Umbra's user base. Currently, we have Piston set to handle 64 request processes concurrently, with each request having a maximum runtime of 3 seconds on the server. This means that within any 3-second period, we can handle up to 64 concurrent requests. Based on our current and anticipated usage of Umbra, which is right now anywhere from 10 to 200 concurrent users, this limit facilitates a good user experience with no noticeable impact to performance across that range. Should we need to scale that server up in the future, we're in a good position to do so. To horizontally scale, we would start by creating additional code execution nodes and employ a load balancer to route traffic between them with no need for shared state across those nodes. Next, let's look at the user authentication service. User sign-up, authentication, and authorization is handled with an AWS resource called Cognito. Given our service-oriented architecture and emphasis on separation of concerns, we wanted a discrete backend service for sign-up and authentication. We chose to use Cognito for 2 reasons. First of all, Umbra's requirements for user sign-up and authentication are standard and relatively uncomplicated. So it made sense to use a vetted third-party service instead of writing our own. And second, as an AWS managed service, Cognito takes care of automatic scaling and any persistence setup required for management of user information. Moving on, let's take a look at the collaboration service that Bethany mentioned earlier. This is Y Suite deployed to Cloudflare workers. This server is by far the most heavyweight in both compute and memory consumption, and requires the ability to respond to variable workloads given the number of users, rooms, and frequency or complexity of input from those users. For this reason, the collaboration service is set up to scale automatically, utilizing Cloudflare's workers and durable object resources. Cloudflare workers are a serverless execution environment for running the logic of Y Suite, and durable objects are an in-memory state solution that the workers use for data persistence. The collaboration service spins up as many Cloudflare workers as are required to handle user input and conflict resolution, and as many durable objects as are necessary to persist the state of Umbra's rooms for the length of user sessions. Finally, let's take a look at the database. Umbra's code library functionality allows authenticated users to save blocks of code by persisting them to a Postgres database. We opted to use Amazon's RDS to handle management of the database server. While a NoSQL database could also have worked, Umbra uses a relational database to enforce a structured schema on a fairly simple relational data set. The primary purpose of our database is to associate users with their saved code blocks. This schema structure is uncomplicated and is unlikely to change, so we favored the schema validation and ACID compliance of a relational database over the flexibility of NoSQL. Vertical scaling is straightforward with RDS, but even if we were to grow to the point of needing horizontal scaling in the future, we could do so without major departure from our current architecture. This is made possible because RDS supports automated read replica creation, with read replicas being created based on database workload metrics. I hope this tour of Umbra's services and architecture are helpful in giving insight into how Umbra works and how it can be scaled. On a personal note, our team greatly enjoyed the challenge of creating Umbra, starting from an idea to a first line of code on a code editor to a production scaled distributed system. We couldn't have done it without the remarkable capabilities of our team members. And for this, we owe a great deal to the years we spent mastering the curriculum provided by Launch School. I'd like to express particular gratitude for the direct and indirect contributions of Nick Miller, Sergeant Korich, Pete Hansen, Max Hawkins, Missy Lovegren, our project mentor, Daniel Liu, and of course, Chris Lee. Thank you. Now we have time for some questions, and if you want to submit a question, you can click on the Q&A box at the bottom of your screen and write one in there. So I'll just wait for the first one to come in here for a while. The first question is, how did you come up with the name Umbra? I can answer that. Well, we vetted a lot of different names, and Umbra sounded cool, so that's the main thing.
Basically.
There's also some tie-in to the idea of collaboration, because an Umbra is the innermost part of a shadow. If you have like 2 light sources casting shadows, then the overlap is the Umbra, so there's like a little bit of connection to collaboration there. But mostly it just sounded good. Okay, so Will has a question. This project touches on a ton of different technologies, real-time, CRDT, code execution, etc. Did any of these end up being unexpectedly challenging to get working? I'll leave that one open for the team.
Which one of those? I'll throw some information out there. While they all sort of have their different challenges, what I felt was the most complicated to get into was everything around collaboration and CRDTs, right? And in conflict resolution. All of that was just, there's a lot of sort of ancillary related things you have to learn in that area to get a good understanding of some of that. And it just took a lot of deep diving. The rest of these parts, which is code execution, it took some research into, trying to figure out the best way to safely execute code in a way that, we could handle with our time frame. But yeah, my personal feeling is that the whole CRDT and using YJS and how that all ties together with real-time collaboration was the most challenging for me to get a full grasp on.
Yeah, and just piggybacking on that, yeah, using YSuite, looking into kind of, the details of it deploying on Cloudflare's edge was, just a little difficult because seems like it's a relatively new technology to be doing code execution at the edge, and the documentation was a little sparse. So just even understanding about, where the durable object is created and, how it's positioned kind of closest to which users, details like that were a little bit difficult, and we had to kind of dig in forums to kind of get answers for that. And I think kind of in tandem with that, the YSuite code base, it's using, WebSocket, so it's using JavaScript on the client side, but, the code for compiling to WASM and deploying on the Cloudflare edge, was all written in Rust. So I ended up kind of ordering a Rust book and speed reading it, and then kind of diving in to try to, understand the code, just to, have a clearer picture of what was happening under the hood. And so we could kind of debug a couple things.
So Mai has a question. How many AWS instances of everything is in your system design? So with our current main deployment, we have two managed services, right? Amazon RDS and AWS Cognito. And then we've got the serverless auto scaling set up on Cloudflare. But for discrete instances, our web server and our code execution server are hosted on individual Lightsail nodes. So I guess the answer to that would be two. We have actually done some alternate deployments where we've moved everything over to individual nodes that are EC2 nodes or DigitalOcean droplets, and that also worked really well. And we were surprised by how much traffic that could support, even with fairly lightweight as far as system resources like bare metal VPSs. So we're definitely like exploring that, and I think it's an open-ended question, like how we would really want to scale in the future. But at present, we have two different discrete instances of AWS Lightsail. And then our next question is, how did you determine the 64 simultaneous execution limit, and what happens beyond that?
Yeah, that's actually that's the default that our code execution engine piston is set to, and we didn't change it. For each one of these processes, it's creating a new thread. I didn't dive deeper into capability wise, what's a typical expectation for creating new processes like that in the operating system. But I guess, the more that gets created, the greater, resources get used. And beyond that, we didn't dive too deeply into that. We just sort of left it the default. We know that we didn't want to try to push that. So I don't have much of a better answer for you than that, but just that was sort of the recommended
Yeah.
default. Yeah.
Yeah. So I think
Sorry.
another thing about that is, like Fred said, we were kind of, everything was working smoothly. We tested and we're kind of happy to leave it there, but also thinking just a little bit in terms of our imagined user activity. So each process, each code execution process is also currently set to, I think, a 3-second runtime maximum. So we were thinking like, how often are there going to be 64 people pressing like run this code within the same 3-second period? And at this point, even, we have one node for code execution, so it'll be all happening on one machine. But in this point in Umbra's life, it seemed reasonable to us to expect that, like 64 executions within any 3-second period would be more than enough. And so far that's not been a problem. But I think that what happens beyond that would probably be determined by what our sort of horizontal scaling automation was. Yeah, that makes any sense.
Yeah.
Next question is from Jason. Can you expand on a fork bomb being a security threat to attack your system?
Yeah, I can. Yeah, I'll tackle that one as well. Fork bomb has a, it looks cool. The text for it looks cool, right? It's interesting. Um, it's essentially, I believe, like a denial of service attack. So it's where a process just keeps replicating itself until every time it replicates itself, it's using up more and more system resources to do so, and it just keeps doing that until your system like your memory or your CPU usage is maxed out, and then your system becomes unstable. Yeah, I believe it does that. Like the way they work, it's just a clever way of writing some code, and I think at least the Linux version I've seen is it's like the code is structured in a way to where you're defining a new function where the name is like a colon symbol is the name of the function, and the definition for that function has it invoking itself and passing its own output to itself, and it somehow spawning a new, like a new child process every time it does that. So if there's nothing to stop that, it just keeps going and going and going, spawning new instances of itself until your system, becomes unstable. I think I think generally, I think, distributions like Ubuntu have limitations in place for the amount of processes that any user can run by default. That sort of stops that thing in its tracks, because the operating system itself won't allow X number of processes being simultaneous run by a specific user. So it kind of, I think for the most part, there's a lot of built-in protection against that now, at least in some places.
Okay, next question is executing code from various different users seems intrinsically risky. Was isolating the different users something you got for free from the Piston library, or was that something you needed to take extra precautions around? Yeah, I mean, it is something that we get for free from Piston. We went through, an iterative process and figuring out what learning about what the security considerations are with our needs for the project, and starting from basically a node runtime, we moved on to a different sort of more sandboxed code execution environment called Dino. And then one of the reasons that we chose Piston is because they've very much prioritized like figuring out security sandboxing to a degree that we could not have hoped to do in the time that we had. I think they have a bug bounty program where nobody's ever managed to like crack their sandbox in the 2 years that it's been open or something.
Yeah, they have an open
Check me on
challenge
that, Fred.
Yeah, that's yeah. That was one of the big,
they had done more than we had time to do. So
right.
that
So
much
it's like,
was obvious.
Yeah, we tried a couple different options here. We're looking at things and they had their pros and cons, and then we came upon Piston, and it was just highly engineered specifically for this purpose. And after seeing all the built-in, security precautions that it's taking, and this open challenge to, hey, try anything, throw anything at us, come take us down. And as that would happen, they would incorporate those, those problems into their new code and update it to address these security concerns that people would find. And I think, the last time when I had at least as of that update I read about, they had been they had a running instance up for over 2 years and nobody could take down. So we're like, okay, we're not going to beat that, like I mean, that's, we were really aware of trying to make the code execution as secure as possible, to keep bad things from happening. And it's like, when we came upon that, we're like, okay, this is like, why not? This is too great. We're not going to beat this,
Wait for another minute here, see if there's any more questions. Otherwise, thanks for coming to our talk.
Yeah, thank you.
Any
so
last
much,
questions?
everybody.
Oh, Will has a question.
Curious if you have any weak links in the project architecture that you'd like to improve on, and or if there are any specific technical solution that you're particularly proud of. What's everybody's thoughts on that?
I'm thinking.
Yeah, that's a great question.
Yeah.
I'm particularly proud of, sorry, go ahead, Bethany, if you want to.
No, please, Michael, go ahead.
I'm really proud of like how atomized our system architecture is. The fact that, our initial iteration of it and the current main deployment of it is running on, light sail instances or whatever. But in a weekend, it was possible to go ahead and like port all this over to like bare metal VPSs. I think speaks to the thought that went into making sure that everything was kind of like atomized and that we really delivered on the separation of concerns and scalability aspect of things. So working with a distributed system was like really cool, and I think we executed well on that. So I'm particularly proud of that portion of things.
Yeah, and I think, one thing that stands out to me too is the with the durable objects serving WebSocket, as a WebSocket connector for the rooms, I'm eagerly awaiting for support for hibernation in Rust. Because it turns out if people leave the tab open, the building,
Don't tell them that. No, I'm just kidding.
I know. But yeah, just waiting for hibernation to come to Rust. Eagerly awaiting that because it's present in JavaScript. People aren't active on a tab, it'll shut the connection down, and the billing on demand shuts down. So yeah, hopefully in the next month or so we can, get that merged in, and yeah, I think that will be a great improvement.
Yeah, I was jokingly saying, but yeah, you want to raise our bill up, go ahead and just leave some open tabs.
Yeah.
Leave sessions open. Yeah.
Yeah, I think building on that, just one of the really interesting things about this project was just that there are a few different components, and I think the whole time, or especially at the beginning of the process, we were kind of weighing the options between, building the service ourselves from scratch and versus using, an open source project that we had researched and found that was kind of doing these things. And part of that was linked to the time frame that we were working with. And I think at this point we could build one of those, some version of any of those ourselves from scratch, given the time. But at the beginning, it was this interesting balance between getting up to speed quickly on the domain. And at that point, it was just, okay, we're either going to build this ourselves or we're going to learn, Y suite from inside out. So that's interesting. And I think personally, it makes me really curious to sort of, I don't know, to build an alternative to Y suite or even, something akin to Piston. Those each would have been, projects on their own, but I think we all have developed a lot of knowledge around, through experience with those technologies. So it'd be interesting then to sort of personalize or fine tune things the way that we would want.
Okay, so last question, and then we'll conclude. How did it feel working together as a team for tackling this problem?
Who wants this one?
Yeah,
You know?
I thought it was great. Yeah, I mean, we were able to kind of find, divvy things up and find, like Fred had energy for the code executions. He was diving into that. You know, Bethany was sort of helping me look at Cloudflare, and Michael was helping with system design. So it was really fun to have, find our individual energies and kind of like, keep each other in the loop and just kind of like play off each other, right? So that group dynamic really helped kind of give energy to the process and just made it kind of, a fun process throughout.
Yeah, just to expand a little bit on that, David. Yeah, it's we did, we had the kind of the luxury of knowing each other to some degree a little bit before we were formed as a Capstone team. So we had some idea of what kind of personalities we were getting in we were going to get, right. The pressures of the sort of Capstone experience, it can bring out uh traits in people that are not always great, right. Everybody's in a pressure cooker together. And so that there are some challenges, but it was really helpful to be able to have a sort of testing ground for this sort of challenges. Working with people in a team in a high pressure or what feels like a high pressure situation, and learning to navigate that. Navigate the whole process together. And no, at the end of the day, I love my team. I wouldn't have changed anything, and I had a lot of fun doing it.
Yeah, I would say not having developed software in a team before and coming from a sort of mental model that was developed from like total self-reliance of the years of going through the curriculum, it was initially uncomfortable, but also kind of thrilling to realize like how much of a force multiplier having 4 really capable people paddling in the same direction was. Because once we got rolling, it was just an absolute, unstoppable train of production. And to see like how much can be accomplished so quickly in that team environment is thrilling and scary and very cool. And I'm glad that I got the opportunity to get a firsthand experience of what that's like before working as a dev.
Yeah, absolutely. Yeah.
Yeah.
All right, that's all we got.
All right.
Thank
Thanks
you everybody
everybody.
for
All
coming.
right.
Yeah.
Thanks for coming.
All right.